So the next plenary speaker is Tomoyuki Suzuki, son of Sony Corporation in Atsugi, Japan. And the title of the plenary talk is Challenges in Image Sensor Development. Suzuki-san received his bachelor and his master degree in electronic engineering from Shizuoka University, Shizuoka, Japan, of course, in 1977 and 1979, respectively. He joined Sony Corporation in 1979, and he was involved in the development of the CCD. And it's a very nice coincidence that we have Suzuki-san now speaking as a plenary speaker right after Lou Thurman introduced us to the CCD, being the Nobel Prize winners, or at least Boyle and Smith, who invented the CCD. From June 2004, Suzuki-san has been the Senior Vice President and Corporate Executive of Sony, where he is also the Deputy President of the Semiconductor Business Group. His expertise is in image sensors, as I mentioned already, and image signal processing. And his current goal is to focus on developing sensors with improved performance and technology. Please join me in welcoming Suzuki-san of Sony. Success.
Thank you. Good morning, everybody. My name is Tomoyuki Suzuki from Sony Corporation. I have been engaged in the image sensor business since joining Sony over 30 years ago. The title of my presentation today is Challenges of Image Sensor Development. I would like to talk about the history, the current situation, and the future prospects of image sensor. Steady advancement in semiconductor technology have created many types of audio and video products. The digital camera represents this trend well, where strong market growth was driven by image sensor evolution. Today, I will discuss the achievement of image sensor development and the corresponding advance in digital cameras. The first subject is exceeding film quality by CCD image sensor. And the second subject is exceeding human vision by CMOS image sensor. Further, I will elaborate on the future of digital cameras, illustrating the way that image sensors are driven camera growth. I will talk a little about the digital camera history. The camcorder was the pioneering consumer product using image sensor from the 1980s to the middle of the 1990s. Then, the wide use of personal computers, enhanced memory capacity, and high-speed data processing created a positive environment allowing for the rise of the digital still camera, abbreviating DSC, in the second half of the 1990s. This convergence allowed people to take photos, easily store them, and easily print them whenever they wanted. Following the popularity of the DSC, the cell phone camera appeared early in the 21st century and grew to a 1 billion unit market. In the future, the expansion of the broadband network and the evolution of CMOS image sensor will lead to many diverse cameras, and the market will expand even more. Let me start by describing the evolution of the CCD image sensor. In developing the CCD, the goal was exceeding film quality. The CCD was invented at Bell Laboratories in 1969. Just last year, the Nobel Prize was conferred on Dr. Boyle and Smith. I extremely appreciate two doctors. The history of CCD invented shrinking the chip and increasing the number of pixels by the reduction of the pixel size. Today, I'll explain the picture structure trend of the CCD, and I'll discuss current CCDs by showing their performance. A CCD consists of a photodiode, a device for transferring electrons, and a readout circuit. Currently, interline transfer CCD is widely used in consumer digital cameras. This results from the fact that interline transfer CCD has the potential to save space and to eliminate mechanical components compared to the frame transfer CCD. However, the pixel structure in interline transfer CCD is more complex than other CCD architectures because each pixel must have a photodiode and a vertical shift register, making it a challenge to realize smaller pixels with higher performance. I now introduce the typical pixel structure of the CCD image sensor. P-well is formed on the N-type silicon substrate, and the sensor part is made there. The surplus electric charge, which occurred by the blaze light incidence, is passed from the sensor to the substrate through the P-well. So this structure is called vertical overflow drain. The introduction of vertical overflow drain structures led to greatly improved aperture ratio and electric shutter function, which allowed for the shift from mechanical to electronic control of exposure time. To fabricate the vertical overflow drain structure, an N+ region of greater than 3 micron depth was needed to keep sensitivity high. It is possible to say that the evolution of CCD image sensor is a history of shrinking the pixel. Even if you use the same optical format, by reducing pixel size, you increase the number of pixels. This gives you improved resolution. In this slide, I have illustrated a pixel size and the number of pixels on every optical format since 1996. The present minimum pixel size is 1.43 micron, as 2.3 type is the normal optical format in DSCs. 1.43 micron pixel allows us to make 14 megapixel CCD. When using a 3 micron pixel in the case of the 35 millimeter full-size optical format, 100 megapixel is possible. If this number of pixels were used for the improvement of the characteristics, besides the resolution, a high-performance camera might be made. When reducing a pixel, the sensitivity declines in proportional to the pixel size. Currently, CCD pixel size is 1/100th of that used in CCDs in 1987. Though the pixel size has decreased, the image quality was maintained by increasing the per unit area pixel sensitivity by a factor of 100 over 20-year period. The developmented technologies were on-chip color filter, on-chip micro lens, tungsten sealed, and so on. In order to create a DSC with a better resolution than film cameras, CCD pixel miniaturization and improved resolution were needed. From the late 1990s until now, the number of pixels increased by 1 to 2 megapixels per year. Today, pixel dimensions of less than 2 microns have been achieved with 12 megapixel DSCs now on the market. As for the transfer electrode structure, which composes a pixel, a wide range of improvement was accomplished to reduce the pixel of the CCD image sensor. In the time when the pixel size was more than 2.35 micron, the transfer electrode structure was composed of multiple polysilicon. When it became 2.2 micron generation, it was composed of single-layer polysilicon to suppress the thickness of the electrode and to improve the sensitivity. At the 2.03 micron generation, initially to ease polysilicon resistance and expand a window of the sensor, polysilicon wiring was laid on the horizontal direction. Thereafter, to realize high-speed drive to read out more than 10 megapixels and to take a moving image, the material of the wiring was changed from polysilicon to tungsten. The cross-section of horizontal direction of the pixel in the CCD image sensor are shown. The light gathering ability was improved by an on-chip microlens by more than twofold. In addition to this, inner lens structure was introduced in smaller pixel using a simple convex shape. And then, in order to make the overall light gathering better at much smaller pixel sizes, the structure was improved to a combination of convex and concave shapes. Also, to reduce the pixel size, the height of the on-chip lens must be made lower so that the sensor can capture incident light efficiently. The pixel, which was 3.275 micron in 2000, was reduced to 1.68 micron in 2007, and the height of on-chip lens is reduced from 6 micron to 3 micron. The sensitivity for the unit area improved with this. This slide shows the vertical cross-sections of the transfer electrode in CCD image sensor. The thickness increases because of the polysilicon overlaps in the case of multiple layer polysilicon. However, in the case of single layer polysilicon, a thin layer is formed because there is no polysilicon overlap. As for the structure, which is laid wiring on the horizontal direction, the thickness of the layer becomes even thinner because the wire is easing the resistance. Here, I show the characteristics of the 10 megapixel CCD image sensor which was developed in the way I have explained. The optical format is 1.2.3 type, and the pixel size is 1.68 micron. In the still mode, the speed of reading out is 2 frames per second in the 10 megapixel. In the movie mode, 720p can be read out in 30 frames per second. To suppress a more layer effect by the movie mode, the 2 same color pixels on the horizontal direction and 3 pixels on the vertical direction are added. There are also excellent characteristics of the saturated signal, the sensitivity, the smear, and so on. Today, over 100 million DSCs, which have such CCDs, are sold per year. While increasing megapixel count for CCDs in DSCs, development of advanced hot system size, abbreviating APS size CCDs for DSLR, was also proceeded with. As for 10 megapixel CCD image sensor, I now show a comparison between CCD for DSC and CCD for DSLR. An APS size CCD has 13 times greater pixel area than that needed by CCD for DSC, so the characteristics of CCD for DSLR is so excellent that it cannot be compared with CCD for DSC. However, it's not easy to achieve electron transfer and chip characteristic uniformity because of the much bigger chip size. Through improved semiconductor technology, an APS size CCD for DSLR was commercialized in 1999. Thereafter, the DSLR camera market grew rapidly, and more than 10 million DSLR cameras are expected to be sold in 2010. I now show a comparative image between CCD for DSC and CCD for DSLR. When expanding the part of the color chart, it is clear that signal-to-noise ratio in CCD for DSLR is better than CCD for DSC. As a camcorder and DSC reaches small size with high megapixel resolution, and as DSLR achieved high image quality and high functionality, it can be said that CCD development has indeed reached the goal of exceeding film quality. Next, I describe the development of CMOS image sensor. In developing the CMOS image sensor, the goal is exceeding human vision. In the 1990s, various CMOS image sensors, which incorporated in pixel transistors, were developed. Compared to CCDs, CMOS image sensors provide the advantage of ease of system integration, low power consumption, the freedom of device architectures. On the other hand, CMOS image sensors have some drawbacks, including increased noise and reduced sensitivity. Correspondingly, the next challenge was to overcome these drawbacks and to realize cameras which exceed human vision. Looking at various applications, cell phones, camcorders, and DSCs are all moving to adopt CMOS image sensor. Cell phones have now become a major application for CMOS image sensor. Since high megapixel CMOS image sensors were developed, anyone can enjoy still photos on his own cell phones. We are very pleased with this. As for the camcorder, the introduction of the CMOS image sensor is moving ahead with high-definition camcorder and the net-connected camcorder. Going forward, we expect CMOS image sensors to become more common in DSCs. At first, I introduced the basic architecture of the CMOS image sensor. They are a current parallel amplifier method and a current parallel ADC method. Most cell phones use CMOS image sensors instead of CCDs because of the high system integration achieved by CMOS image sensors. The ADC and controller driver are on chip, so a very compact camera can be made for cell phones. In addition, the reason the CMOS image sensor is adapted by the high-definition camcorder is that CMOS image sensors provide low power consumption and high-speed readout. This performance is also achieved by system on chip. The CMOS image sensor has many advantages, such as system integration, the degree of freedom of the reading out, and low power consumption. In addition, developing these CMOS advantages, the areas where CMOS still runs CCD must be improved. Therefore, the key points of CMOS image sensor development are pixel shrinkage, increased sensitivity, decreased noise, and increased readout speed. I now show a comparison of pixel pitch trend of the CMOS and CCD image sensor. The CMOS image sensor pixel is shrinking faster than the CCD image sensor pixel these days. In 2009, CMOS image sensor realized the pixel, which is smaller than CCD, by achieving 1.4 micron. The technologies to support pixel shrinkage are, firstly, decreasing the number of transistors in the pixel, and secondly, guiding the incident light to the photodiode effectively. The CMOS image sensor consists of transistors and a photodiode. To realize CMOS image sensor, in addition to photodiode, 4 functions are needed. They are control of the amplification, the select, the transferring, and the reset. Because each function is assigned to one transistor, there are 4 transistors per pixel. The number of the transistors per pixel can be decreased by sharing those transistors. Therefore, we achieve 1.75 transistors per pixel and shrink the pixel size. Improved light gathering to the pixel has been the major factor in image sensor advancement. When the pixel pitch is under 2 micron, the incident light is partly blocked by the wiring layer in the pixel. To expand a window or decrease the thickness of the wiring part, the material of the wiring was changed from aluminum to copper. By this, the thickness of the wire part decreased by about 40%. I now show the sensitivity comparison between the aluminum process and the copper process. The sensitivity of the copper wiring was improved about 20% at the length of f2.0 compared with the aluminum wiring. By combining CMOS image sensor with the copper process and f1.8 high magnification zoom lens, a high-quality camcorder was realized. Next, let me discuss frame rate. In the case of CCD for DSC, the number of pixels increased, but the frame rate declined. Because the CCD frame rate is about 2 to 4 frames per second, it is difficult to capture the moment when taking photos. By comparison, CMOS image sensors can have faster frame rate. To increase frame rate, power consumption must be decreased. I now show the comparison of power consumption of CCD and CMOS image sensor at 60 frames per second. When outputting 60 frames per second in 2 megapixel, the power consumption exceeds 1 watt in CCD image sensor. By contrast, the CMOS image sensor consumes less than 1/5 of this power. Thus, when reading many pixels at high speed, the CMOS image sensor is absolutely favorable. To read many pixels at high speed, a low-noise column parallel ADC architecture was developed. Analog and digital dual correlated double sampling, abbreviating dual CDS, realizes low noise and high speed with a few analog circuits. By canceling the signal deviation on each pixel through dual CDS, high-speed readout with low noise has been achieved. This has led to the new concept of a camera that can achieve high-speed continuous shooting and that can do both video and still photo application. I now show the timing chart to read out the signal from the pixel. At first, an image signal from the pixel is inputted to the comparator. After reference signal is changed to the digital signal, the image signal is changed to the digital signal. A digital image signal and the reference signal are then subtracted. An analog to digital conversion for one line, which has thousands of pixels, is completed within several microseconds by this method. Because imbalance of the offset at the comparator can be cancelled, the line defect of vertical direction is removed. Thus, high speed and low noise are achieved at the same time. To return to the topic of frame rate, a low noise column parallel ADC architecture with dual CDS achieved high speed and low noise in CMOS image sensor. The CMOS image sensor frame rate is over 20 times higher than the frame rate of a CCD. This is an example of taking a picture by 6 megapixel at 60 frames per second CMOS image sensor with column parallel ADC. When taking high-speed image at 60 frames per second, the one frame of moving image becomes a high-precision still image. It is possible to say that the video is a set of the high-precision still images. Let me now talk about advances in sensitivity. Our back-illuminated technology allows for this advance. In the conventional CMOS image sensors, the incident light first passed through the on-chip lens via the color filter, then passed the metal wiring, reaching the silicon. Where it was converted to electrons. Since the wiring thickness is a few microns, it is thicker than the area of the pixel, reducing the light available for conversion to electrons in the silicon. Thus, using the opposite side as a surface for light exposure allows for the light to reach the silicon more efficiently. This back-illuminated structure is obtained by grinding the silicon wafer to a thickness of a few microns after back-end-of-line process. In realizing the minute pixel and the sensitivity, which exceeds CCD image sensor, the goal was to use a back-illuminated CMOS image sensor in a DSC. In the development of the back-illuminated structure, there were some problems. For example, wafer and assembly process, the reduction of crosstalk, and the reduction of dark current. To reduce the crosstalk, we inserted a metal shield between pixels for the light crosstalk. We adjusted the microlens shape and adjusted the impurity distribution in the hot diode. To reduce the dark current, we decreased the defect and optimized the process of the hot diode. This slide shows the spectral properties of back-illuminated CMOS image sensors. Because of the reduction of crosstalk and the dark current, the spectral properties of back-illuminated CMOS image sensor are the same as the conventional structure. These images compare a back-illuminated CMOS image sensor and the conventional sensor in the case of the low-light subject. As for the low-light illumination, the back-illuminated CMOS image sensor has much higher signal-to-noise ratio compared with the conventional sensor. The image taken by the back-illuminated 2.3 type 2.3 megapixel CMOS image sensor with 1.65 micron pixel is shown. Because the back-illuminated CMOS image sensor can realize the spectral properties which are the same as the conventional for the full screen, it achieved a good color reproduction in the center and the periphery of the image. Performance of the back-illuminated CMOS image sensor is shown. The back-illuminated CMOS image sensor has higher sensitivity and lower noise compared with the conventional. Because the lens's F-number dependence of the sensitivity is good, the lighter optical lens can be used effectively. The dynamic range and the dark current are very good too. So now, we have arrived at the point where the CMOS image sensor is on its way to exceeding human vision, realizing both high-speed performance by the parallel ADC and high resolution with high sensitivity by the back-illuminated structure. Now let me talk about future trend. In the future, the broadband network capacity, data storage volume, and data processing speed will all continue to increase. The resulting abundance of data capacity will allow for more pixels, greater picture frame rates, and wider dynamic range, allowing for excellent images to be viewed. In this phase, the digital camera can achieve a level which exceeds human vision. Furthermore, the evaluation of the CMOS image sensor will lead to super reality and new image functions for cameras in the future. There is a limit at which the human eye can perceive illuminations, speed, and the distance of an object being photographed. This limit can be exceeded by evolving CMOS image sensors to enhance spatial, temporal, and dynamic range characteristics. When thinking of the structure and architecture, CMOS image sensor will continue to evolve. To be specific, looking at this slide, 4K by 2K video capture, less than 0.1 lux video capture, and 1000 frames per second high-speed capture are the current performance targets. These will be achieved using CMOS image sensor technologies that include the power-reduced and multiple-bit ADC, improvement of dynamic range, and signal-to-noise ratio via back-illuminated structure. The high-resolution still image and high-speed movie image will be fused perfectly in the new digital camera world. In addition, we envision a super reality which creates a new image expression. The first thing is the ultra-high speed, where still images with high resolution and no distortion will be extracted from a fast-moving image. A smooth through motion image of very quickly moving subjects will be reconstructed. By evolving the column parallel ADC to high speed and lower power consumption, an ultra-high speed CMOS image sensor will be realized. The second of super reality is global shutter. Because the pixel is laid out in sequential order in the current CMOS image sensor, a distortion occurs in the image when shooting a fast-moving subject. Global shutter can allow us to extract a still image with high resolution and no distortion from a fast-moving image. The pixel structure is very complicated in global shutter because the electric charges have to be let out from each pixel and save it into the memory in the pixel at the same time. However, global shutter is an indispensable technology to realize super reality. The technology which realizes the following super reality is a wide dynamic range. In industrial cameras, by spatially varying exposure or multi-sampling exposure, the dynamic range is improved from 60 decibel to 120 decibel. As of now, a regular CCD in a consumer digital camera does not have such dynamic range. However, a white overflowing part and a black surrounded part in the image by a normal CCD are improved to be reflected by the CMOS image sensor with a wide dynamic range. In the near future, such type of improved wide dynamic range feature will be part of even consumer digital cameras. Next super reality is bokeh, in other words, out of focus. Bokeh occurs for parts of the scene that lie outside the depth of the field. Photographers sometimes deliberately use a shallow focus technique to create images with prominent out-of-focus regions. A cinema-like image will be captured whereby the object being photographed is the center of attention and the background is intentionally unfocused. This emphasizes the subject while defocusing the background. Let me introduce two functions for the future. One is creating a 3D image. At present, various manufacturers are releasing 3D displays then the digital camera to create excellent 3D image easily will be achieved by improving CMOS image sensors. A camera which makes 3D imaging possible by combining a relay lens and two image sensors has been already developed. When this feature is achieved on a single CMOS image sensor, it is possible to be implemented in a consumer digital camera. The other new function is an image sensor like eyeball, in other words, a spherically shaped image sensor. The technology for grinding the silicon wafer to a thickness of a few microns was established by development of the back-illuminated CMOS image sensor. By using this thin wafer, a CMOS image sensor can be bent into a spherical shape. Consequently, the shape of the CMOS image sensor can approach that of an eyeball. In this way, the composition of the optical lens will be simplified and it will become easier to capture a wide-angle image. Today, I talk about the history of the past to the present and then the future prospect of the image sensor. The achievement of CMOS image sensors with optical lenses and camera signal processing paved the way for a new imaging world. This is a world in which human vision is exceeded, and a world where a new image expression is created. The new imaging world will bring more enjoyment, pleasure, and excitement to all people. The new digital camera world which we aim at is beyond the space, beyond the time, anywhere, anytime, we can enjoy a super realistic image all over the world. To realize this, the evolution of CMOS image sensor is indispensable. There are many problems to be solved, but the evolution of CMOS image sensor has the possibility to be infinite. Because of exceeding film vision, we can see what until just recently we could not see. Let's realize such a camera by the image sensor evolution. Best wishes to all of you, and thank you for your attention today.